Welcome to our lecture on ring theory. Today, we are going to explore a fascinating and foundational concept known as unique factorization domains. If you have ever wondered whether the fundamental rules of arithmetic hold true when we move beyond ordinary numbers into abstract algebra, this is exactly where we find the answer. We will build this understanding from the ground up, so let us dive right in. To begin our journey, imagine you are building a toy house out of plastic Lego bricks. No matter how you assemble a specific wall, if you break it down into its absolute smallest indivisible Lego bricks, you will always end up with the exact same pile of bricks. You might take them apart in a different order, but the final count of red, blue, and yellow bricks remains identical. In mathematics, we love breaking complex objects down into their simplest building blocks to understand them better. A unique factorization domain is simply a mathematical universe where this beautiful, predictable Lego brick property holds true for abstract algebraic objects, preventing mathematical chaos. Now that we have our Lego analogy, let us establish the formal rules of our mathematical universe. We start with an integral domain, which is just a commutative ring where multiplication order does not matter and it has no zero divisors, meaning you cannot multiply two non-zero things and get zero. Inside this universe, we must ignore units. Units are simply elements that have a multiplicative inverse, like 1 and -1 in the integers. We ignore them because multiplying by 1 does not fundamentally change a number's building blocks. This sets the stage for finding our true indivisible pieces. Building on the idea of ignoring units, we need to define what our actual building blocks are. We call these irreducible elements. An irreducible element is a non-zero, non-unit element that cannot be factored into two smaller non-unit pieces. It is the algebraic equivalent of a prime number. Finally, we define associates. Associates are two elements that only differ by a unit multiplier, such as 5 and -5. Recognizing associates is crucial because it allows us to see when two seemingly different building blocks are actually the exact same piece, just wearing a slight disguise. With our building blocks defined, we can finally state what makes a domain special. A unique factorization domain, often abbreviated as a UFD, is an integral domain where every non-zero, non-unit element can be factored into a product of irreducible elements. But it does not stop there. Furthermore, this factorization must be strictly unique. This means if you find two different ways to factor the element, they must actually have the exact same number of irreducible factors, and those factors must just be associates of each other in some order. This guarantees absolute predictability in our algebraic system. Let us translate this concept into a mathematical formula. When we take a non-zero, non-unit element, which we will call A, we want to break it down. The formula shows A equals P1 times P2 all the way to Pn. Here, the symbols P1 through Pn represent the irreducible factors, which are the indivisible building blocks of our ring. The subscript n simply tells us the total count of these irreducible pieces. Conceptually, this formula states that our starting element can be successfully dismantled into a specific, finite number of fundamental parts. If n increases, it means the element is made of more building blocks. This formula we just saw leads us to an important question. What if someone else factors the exact same element? Suppose they get A equals Q1 through Qm. For our universe to be a unique factorization domain, the first strict requirement is that n must equal m. This guarantees that no matter how you break the element down, you will always end up with the exact same total quantity of building blocks. If one person finds 5 irreducible pieces, anyone else factoring that same element must also find exactly 5 pieces. Now that we know the count must be the same, we look at the second condition for uniqueness. The formula Pi equals Ui times Qj defines what we mean when we say the pieces are fundamentally the same. Here, Ui represents a unit multiplier. This tells us that every single building block in the first list matches a building block in the second list, possibly altered by a harmless unit multiplier. As long as the factors only differ by a unit, they are considered associates, and the factorization is officially unique. Before we move on, let us see this with a concrete example, using a universe we already know. We want to show how the number 12 factors uniquely in the integers, demonstrating the UFD property. We are given the number 12 and asked to break it down into irreducible elements, which are our prime numbers. We start with the standard prime factorization. We divide 12 by 2, then 2 again, and then 3. This gives us 2 times 2 times 3. The numbers 2 and 3 are irreducible because they cannot be divided further into smaller whole numbers. This gives us our first valid set of building blocks. Continuing with our example, let us look at a second way to factor the exact same number 12. In the ring of integers, negative prime numbers like -2 are also perfectly valid irreducible elements. Mathematically, multiplying -2 by -2 gives +4, and multiplying that by 3 gives 12. At first glance, this looks like a completely different recipe of building blocks compared to our first attempt. We chose this approach to test the boundaries of our uniqueness rule. We now have two seemingly different factorizations, and we need to see if they are actually the same. Now that we have our two factorizations, let us resolve the apparent difference. We compare the factors and reveal the hidden connection. The number -2 is equal to +2 multiplied by -1. In the integers, -1 is a unit because it has a multiplicative inverse. Because the factors only differ by this unit multiplier, we call them associates. This proves that the building blocks are fundamentally the same. Even though the second factorization looks different because of the negative signs, the rules say we only care about uniqueness up to associates and order. Physically, this means the core structure of the number 12 remains absolutely unchanged. So, we have proven that uniqueness holds for integers. This brings us to a scenario where the rules break down. To truly understand why unique factorization domains are special, we must look at a universe where unique factorization fails. We are going to examine the ring formed by adding integers to multiples of the square root of -5. In this new mathematical universe, we will see that a single number can be broken down into two completely disconnected sets of building blocks. This is a profound realization because it shows us that we cannot always take unique factorization for granted when we move into more complex algebraic systems. Let us put this new ring to the test with a specific example. We are given the number 6, and we want to factor it in two fundamentally different ways within the ring of integers adjoined with the square root of -5. We begin by factoring the number 6 in the most familiar way possible. Inside this specific ring, the numbers 2 and 3 are strictly irreducible. You cannot find any smaller non-unit elements in this ring that multiply together to create 2 or 3. So, our first factorization is simply 6 equals 2 times 3. This gives us our first set of building blocks. Continuing our investigation of the number 6, we attempt to factor it using the complex numbers available in our new ring. We multiply 1 plus the square root of -5 by 1 minus the square root of -5. Why did we choose this? Because using the algebraic rule for the difference of squares, the middle terms cancel out. This leaves us with 1 minus -5, which perfectly equals 6. We have just discovered a second completely valid way to break down the number 6 into irreducible parts. Physically, we have built the exact same Lego house using a completely different set of bricks. To make sense of what we just calculated, let us look at this diagram. You are seeing a visual representation of the crisis we have encountered. At the top, we have our starting number, 6. From there, the diagram splits into two completely separate paths. On the left branch, we see a first factorization, 2 times 3. On the right branch, we see a complex factorization, 1 plus the square root of -5 times 1 minus the square root of -5. In the center, a large red cross clearly marks that these two sets of factors are not associates. This diagram perfectly illustrates the breakdown of uniqueness. Now that we have seen the visual breakdown, let us prove mathematically why this happens. This chunk of the proof is setting out to establish whether the items on the left are just disguised versions of the items on the right. To save the unique factorization domain property, we must check if they are associates. The mathematical reasoning here relies on units. In our specific ring, the only valid units are the numbers 1 and -1. We set up an equation to test if the number 2 can be written as a unit multiplied by our complex factors. This step is crucial to see if a hidden connection exists. Following our setup, we reach the final conclusion of our proof. We evaluate the equation we just built. No matter which unit you choose, 1 or -1, multiplying it by our complex factors will never equal the simple numbers 2 or 3. This inequality is the final nail in the coffin for uniqueness in this ring. It proves mathematically that our two sets of factors are absolutely not associates of one another. Because they are not associates, we have found two completely different sets of irreducible building blocks for the exact same number. This gives the final result that this ring is strictly not a unique factorization domain. Having seen a mathematical universe fail, you might wonder why this matters in the real world. In mathematics and computer science, we rely heavily on the fact that integers factor uniquely. This property is the absolute bedrock of modern cryptography, such as the RSA encryption that secures your bank transactions and internet data. RSA relies on the fact that multiplying two massive prime numbers gives a unique result, and factoring it back is mathematically guaranteed to have only one correct answer. If we worked in a system where numbers could factor in multiple ways, encryption algorithms would completely break down, yielding multiple conflicting original messages. We have covered a lot of ground today, so let us summarize our key takeaways. First, a unique factorization domain is a mathematical space where every element breaks down into a single, unique set of irreducible building blocks. Second, while ordinary whole numbers naturally behave this way, we proved that complex algebraic systems like the ring with the square root of -5 do not. Finally, identifying whether a ring is a unique factorization domain is crucial for guaranteeing predictable behavior in fields like cryptography. You have now mastered the fundamental concepts of unique factorization.